Let me welcome you to this lecture. We have so far discussed the chemistry of metal carbonyl complexes, nitrosyl complexes, dinitrogen complexes, phosphine complexes. We have as well as looked at the chemistry of metal alkyl, metal alkenyl, metal alkynyl, and recently we have looked at the chemistry of metal alkylidene as well as alkylidyne complexes. So if you look carefully at these ligands, that is the carbonyl ligand or the dinitrogen ligand or the nitrosyl ligand, phosphine ligand, and as well as if you look at the metal alkyl complexes as well as the alkenyl complexes or metal alkynyl complexes, or if you look at alkylidyne complexes as well as alkylidene complexes as well as these alkylidyne complexes, there is one common thread among all of these ligands, that is that in all of the cases the ligand to metal electron transfer takes place from an ligand orbital, which is essentially sigma orbital in terms of the ligand atoms. That is, here we see in all of these cases we have looked at the molecular orbital diagram and we have seen that a sigma type orbital of these ligands essentially donate electrons to the metal center, and this forms a ligand to metal sigma bond, of course. Now, in case of these ligands also we have seen that a sigma type ligand of sigma type orbital of the ligands of all of these ligands essentially donate or is involved in ligand to metal electron donation, that is ligand to metal electron donation, and these sigma type orbital donates electrons to the metal center, and this essentially again forms a sigma bond in these complexes formed by these ligands as well. So we will now deviate our discussion from such ligand and we will discuss about ligands which uses a pi-type orbital to donate electrons to the metal center or to form a metal to ligand sigma bond. The ligand uses one of its pi bonding orbital to donate electron from this pi bonding orbital to metal empty orbitals. So such ligands which forms complexes with metals by donating electrons from present in a pi type orbital are essentially known as, or they are categorized as, pi complexes. And examples of such ligands involve olefins when it uses the pi cloud or the pi bonding electrons present in the pi bonding molecular orbital in an olefin when it is donated to a metal to form metal olefin complexes, unlike the alkenyl complexes that we have seen earlier. In this case, the pi bonding molecular orbital is used to, or the electrons present in pi bonding molecular orbital are donated to empty metal orbital, and such complexes we call them as metal olefin complexes. We have discussed about this earlier when discussing the chemistry of metal alkenyl complexes, and they are essentially categorized as pi complexes. Similarly, metallocene complexes or complexes formed by adenes, say this sort of complexes where the aromatic pi cloud in an aromatic compound essentially is donated to a metal empty orbital to form metal ligand complexes, are again they are also called as pi complexes. So during this lecture we will discuss about the chemistry of metal olefin complexes. So the chemistry of metal olefin complexes is essentially very old, even older than the chemistry of metal carbonyl complexes, as the first metal olefin complex was prepared way back in 1827. So it is known as the J salt. It was prepared by boiling PtCl4 with ethanol, and it essentially gave a compound whose formulation is this sort of a compound. And this compound, though it was prepared in 1827, the structure of this compound is only recently known, and people were not able to describe the molecular structure of this compound. How the ethylene is bonded to the metal center here to form a stable complex is only known very recently, and that is why this particular compound, it is called the Jay's salt, was interesting for a very long period of time since its discovery. So now we will discuss about the preparation of these metal olefin complexes, and we will see different methods that are been so far used for preparation of metal olefin complexes. So again, we will categorize this reaction in different types of reaction, and we will discuss about different examples of such different approaches for preparation of metal olefin complexes. So let us look at the first example, that is the first type of reaction, that is essentially preparation of olefin complexes by doing substitution reaction. So the preparation of Jay's salt as well, instead of by reacting with PtCl4 with ethanol, one can also prepare this compound by doing substitution reaction using suitable platinum precursor. That is, if you take K2PtCl4 and then treat it with ethylene in presence of dilute HCl under 60 bar pressure of ethylene, that is at very high pressure of ethylene, so this will essentially result in preparation of Jay's salt in good quantity. And this reaction can also be catalyzed, or the pressure of the ethylene, that instead of using 60 bar, one can use 1 bar ethylene, and the reaction will proceed quickly or get completed within a few hours. If one uses SnCl2 as the catalyst, then 1 bar C2H4 will result the Jay's salt in good quantity in a very short period of time. So it can be catalyzed by such catalyst and by using SnCl2 as the catalyst. So the abstraction of chloride from such metallic salts can be essentially achieved by also using AlCl3, because AlCl3 can abstract the chlorides to form AlCl4. We'll see one example where this is done. That is, if you take this rhenium carbonyl halide complex and then in presence of AlCl3, if you react this with ethylene, then one can replace the chloride by ethylene, and now because the chloride is lost, so the complex is going to be positively charged, and AlCl4 that is going to be formed after AlCl3 abstracts the chloride from the precursor complex over will be the counter anion in this complex. So this is how one can do substitution of halides by using ethylene, and by when AlCl3 is present, then it assists us to remove the halide ligand and then substitute the same with the ethylene to result such metal olefin complexes. So one can also use, instead of AlCl3, other reagents which can replace or substitute the halide ligand. So one such example is AgBF4 or silver tetrafluoroborate. So if you take this, you see this iron carbonyl halide complex, and then if you treat it with AgBF4 in presence of ethylene, again one can replace, or this is the silver reagent will react with the complex here to form silver iodide, which will get precipitated out, and therefore, and then ethylene will replace the iodide ligand over here. So we can draw the resulting complex in this way. So Fe CO CO and the ethylene ligand in this way. So that is how, also again, because we have abstracted the negatively charged ligand from the complex, so this whole complex is going to be positively charged, and BF4 tetrafluoroborate is going to remain as the counter anion here, and that will allow also us to isolate the compound in crystalline form, because this particular anion, this is non-coordinating anion, and it allows one to isolate the products in crystalline form. So that is how it helps, or that is why one uses tetrafluoroborate salt of silver to extract the halide as well as obtain the product in crystalline form. So apart from halide precursor complex, one can also use metal carbonyl precursors where carbonyl ligands will essentially be replaced by olefins, and we have seen examples of such reactions while discussing about the reactivity of metal carbonyl complexes. We have seen how one can use metal carbonyl complexes and treat them with olefins to get metal olefin carbonyl mixed ligand complexes. So let us look at some examples of such reactions. So if you take iron pentacarbonyl and then react it with butadiene, so you do this reaction thermally, that is, you replace the carbonyl ligand by using temperature. So at high temperature and high pressure of the butadiene ligand, one can replace the carbonyl ligands, and this will essentially give us a butadiene complex of iron So this is how a metal carbonyl olefin butadiene complex can be prepared by thermal substitution of carbonyl ligands. So instead of thermal substitution, one can also do photochemical substitution on such metal carbonyl precursor complexes. So you can take CpMnCO3 and then do reaction with an olefin and do this reaction under photochemical irradiation. So then one can replace some of the carbonyl ligands. So one of the carbonyl ligand, to be specific, by using this olefin ligand. So this is not CH3, this is CHO. CHO. This is also going to be CHO then. So rest are all hydrogens. So this sort of a metal carbonyl olefin complex can be prepared by substitution of carbonyl ligand photochemically. So in presence of these metal carbonyl complexes, olefins which are not conjugated may isomerize to give us conjugated olefins, which can then go and bind with the metal center, as well as substitute the carbonyl ligand to give us metal olefin complexes. Say, for example, if you take FeCO5 and if you take an olefin which is not conjugated, So this cannot form diolefin complex. So that is why the complex, this ligand over here or this compound here is going to undergo isomerization to give us conjugated olefin. This sort of conjugated olefin which can now bind with iron to give us a iron carbonyl olefin complex. So isomerization happens because of this is a metal induced isomerization happens during this reaction, and that is how the metal carbonyl complex is essentially formed. So again, this is done thermally. So one needs to increase the temperature to 140 degrees Celsius to obtain the product in this case. So one can also take coordinatively unsaturated precursor complexes, and then upon reaction with olefin, one can get metal olefin complexes. So if you take the viscous complex, that is iridium Cl CO PPH3 2 times, which is a 16 electron complex. So if you react this with ethylene, so now addition is going to take place. Of course, this is not oxidative addition because the olefin is a electroneutral ligand, and that is why the oxidation state of iridium is going to remain same. Only the coordination number is going to increase, and in this case, one will get this sort of a 5 coordinate product after the addition reaction, and the product is of course now 18 valence electron species, unlike the precursor complex, which is a 16 valence electron species. So these are the examples of substitution reaction as well as addition reaction to different precursor complexes, and how one can get olefin complexes by doing this sort of reaction. So we'll now look at other type of reactions that yield metal olefin complexes. So the second approach that we are going to discuss for preparation of metal olefin complex involves reduction of a metallic salt in presence of an olefin. That is, you take a metal salt and you use a reducing agent to reduce the metal to lower oxidation state, and you do this in presence of an olefin, and then one can get a metal olefin complex. So one very popular example of this type of reaction is that if you take nickel chloride and then if you take alkyl aluminum reagent as the reducing agent, we have seen many examples earlier where alkyl aluminiums are used as reducing agent to reduce metal salts to lower oxidation state. And then if you do this reaction in presence of butadiene, so what you are going to get, cyclization of butadiene is going to take place, and nickel is going to get reduced to nickel 0 oxidation state from +2 oxidation state, and what you are going to produce is a very interesting complex of this sort where nickel is in 0 oxidation state and butadiene undergoes a coupling reaction in this way. Now, this compound is highly reactive as the nickel center is exposed from both the top side and bottom side over here, and that is why it is also termed as naked nickel. And nickel is in 0 oxidation state, and it is now one can do reaction with this particular intermediate complex or reactive complex with other olefins to prepare metal olefin or nickel olefin complexes of desired olefin ligand. So if we do reaction with 1,5-cyclooctadiene, that is C8H12, so then what you are going to get is nickel this sort of nickel cyclooctadiene complex or nickel cord 2 we say. Cyclooctadiene is essentially abbreviated as capital COD, nickel cord 2 complex, and this particular complex is a very important precursor complex for, or it is a very useful precursor complex with nickel 0 oxidation state. So it is used very frequently in organometallic chemistry as a source of nickel 0. So this is how one can use metallic salts in presence of reducing agent and react the same with olefins to produce metal olefin complexes. So we'll see one more example or one more variation of this sort of reaction where metallic compounds are essentially reduced in presence of olefins to produce metal olefin complex, and in this case one uses a metal leucine as the precursor complex. So if you take the Cp2 cobalt complex as the precursor complex now. So this is Cp2 cobalt, and then you do reaction with potassium, which is a very strong reducing agent and can reduce cobalt to positive oxidation state, in this case to 0 oxidation state, or plus 1 oxidation state, sorry. So you do reaction in presence of olefin, so then you retain one of the Cp ligand, and the cobalt is going to bind with olefins in this way. And the potassium that is oxidized will form potassium cyclopentadiene in this way. So that is how, this is another variation of this type of reaction where now the metallic salt is essentially reduced and cobalt from a plus 2 oxidation state it is reduced to plus 1 oxidation state, and meanwhile it also reacted with olefin that was present in the reaction mixture to give us a metal olefin complex, and in fact this particular compound is a very useful CpCO transfer agent, because this can, you can use this to transfer this particular fragment. This complex can be used as this fragment transfer agent in different organometallic reactions. So one more example of this type of reaction that we will see where olefin itself acts as the reducing agent and reduces the metal salt to lower oxidation state and produces a metal olefin complex as well. So if you take RHCl3 where rhodium is in plus 3 oxidation state and you react this with ethylene, so rhodium is going to get reduced now into rhodium plus 1 oxidation state, and it will as well bind with the olefin or ethylene here to give us this sort of a metal olefin complex. So rhodium is now reduced, and the reducing agent is the olefin itself. So another very interesting approach to prepare metal olefin complex, or to be specific, metal butadiene complexes, is to use magnesium butadiene as the butadiene transfer agent. So that is Mg butadiene as butadiene transfer agent. So if you take MnCl2 and then you use C4H6, Mg2THF. This can be easily prepared and do reaction in presence of another ligand, that is trimetylphosphine. So now what you are going to produce is Mn, PMA3, this sort of complex where now butadiene is transferred from this magnesium complex to this manganese center, and it forms again complex butadiene complex with the manganese over here. So one more very useful approach for preparation of metal olefin complex used to is the co-condensation of metal vapors with ligands in gaseous state. That is, you can take that is the fourth approach: metal atom ligand vapor co-condensation. In fact, some of the organometallic metal olefin complexes can be prepared only by this particular approach. So in here what one does is that one vaporizes the metal, and then the metal vapor is essentially allowed to co-condense with ligand in gaseous state, and then it is done of course at a low temperature, and then the temperature is in the second stage the temperature is raised, and during this co-condensation process the metal vapors will essentially condense into metal atoms, as well as it will also form metal olefin complexes. So the yield is going to be low, but as this particular approach is allows preparation of some of the very specific metal olefin complexes which cannot be prepared by any other metal. So one example we will see here is that if you take molybdenum in gaseous state and then react into it butadiene again in gaseous state, let us write C4H6, and in the first state you do co-condensation, that is we express it as Cc at minus 196 degrees Celsius. The co-condensation is allowed to happen, and in the second state you allow the temperature to rise to 225 degrees Celsius, and then what you are going to produce is a very interesting metal butadiene complex of this sort. This sort of molybdenum butadiene complex can be prepared by this co-condensation method. There are a couple of more approaches for preparation of metal olefin complexes, and the fifth method involves nucleophilic attack on enil complexes. So that is nucleophilic attack, addition on enil complexes. So if you take a metal enil complex, it is and then do nucleophilic addition, that is there is CH3 over here, there is OCH3 over here, and nucleophilic attack is going to take place on the enil ligand, and it will transform into an olefin ligand essentially. So that is, we will get now this is positively charged because otherwise it is not going to be 18 valence electron species. So then this is OMe, and this is where the nucleophile comes and attacked, and it will come of course from the opposite side of the metal, and this sort of a complex is formed. After the nucleophile attack on the enol complex here, it transforms into an olefin complex of this sort of. So the last method for preparation of metal olefin complexes we will discuss is the abstraction of hydride from metal alkyl complexes. So the sixth method, abstraction of hydride from metal alkyl complexes. So one starts with a metal alkyl complex. Let's take a metal alkyl complex of this sort. So now this particular hydrogen, which is attached to the carbon atom that is coordinated to the marital center, is highly acidic in nature or hydrating in nature, and it can be removed by using a carbocation. So we use the trityl ion over here. So let's take trityl tetrafluoroborate, and this will remove the hydrogen atom as hydride, and the ligand will essentially be transformed into an olefin because of the removal of the hydride over here, and of course because of that the whole complex will now become positively charged because of the removal of the hydride from here by using this carbocation. So this is how this is the last method which one uses or which for preparation of metal olefin complexes, and this essentially brings us to the end of this lecture. And what we have learned during this lecture is about pi complexes, and we discussed about preparation of one particular type of pi complex, that is metal olefin complexes, and we have seen or discussed different methods for preparation of metal olefin complexes. And the first method that we discussed is the substitution reaction on different precursor complexes. So we have seen how one can use the metal halide complexes as precursors and do substitution of halide from such metal halide complexes by olefin to prepare metal olefin complexes such as the J salt. And then we have seen how one can use or replace substitute carbonyl ligand either thermally or photochemically by an olefin ligand to prepare metal carbonyl olefin complexes. We have also seen that one can use the addition reaction on coordinatively unsaturated metal complexes. So addition of olefin will take place on such coordinatively unsaturated complexes to prepare, and it will essentially give us metal olefin complexes of high coordination number. And then we have discussed about another method for preparation of metal olefin complex, that is the reduction of metallic salts in presence of olefins, and we discussed how one can prepare a nickel cyclooctadiene, bis cyclooctadiene complexes by using this particular approach, using alkyl aluminiums as the reducing agent, as well as we have also seen how one can reduce metallocene complexes by using strong reducing agent like potassium. And this essentially we discussed about preparation of a very important organometallic cyclopentadienyl cobalt transfer agent by this particular approach. And then we discussed how one can use olefins itself as the reducing agent for preparation of metal olefin complexes while reducing the metal salt from high oxidation number to low oxidation number in the same process. Then we discussed about another type of reagent, that is the butadiene, magnesium butadiene reagent, which can be used for transfer of butadiene to different metals and that thereby produce metal olefin or metal butadiene complexes. And thereafter we discussed about a very important method for preparation of metal olefin complexes, that is the co-condensation of metal vapor with ligands in gaseous state. And we discussed that this particular method is very important as several metal olefin complexes can be accessed only by this particular approach. And thereafter we discussed about one more method for preparation of metal olefin complex, that is nucleophilic attack on enil complexes, and how the enil ligand gets transformed into olefin ligand by when an nucleophile comes and attack on the enil ligand in a enil complex. And the last method for preparation of metal olefin complexes we discussed is the extraction of hydride from a metal alkyl complexes. So this essentially brings us to the end of this lecture. Let me conclude this lecture with this, and let me also thank you for being with me during this lecture.